Hello, in this video I want to present the ideas and content of the paper Calibrating Agent-Based Models of Innovation Diffusion with Gradients. I'm one of the two authors, Florian Kotthoff. Yeah, and the idea is that you get a rough overview and then you can decide if you want to read the paper or not. So what do we want to achieve? Innovation diffusion. In innovation diffusion, we research how people decide to adopt a new innovation. So for example, when do people buy a new technology, a new smartphone, for example, or what we used here in this paper is when do people decide to buy a PV system for their house to produce their own electricity. So we have some agents that can make individual decisions and they can decide, okay, at this point in time, either I leave my house as it is or I buy a PV system. And then we do not and then we have like the decision of individual peoples, but if we now want to compare it, how good is the model, we need to compare it to empirical data. And the data usually is not for individual people, but like for subgroups. So we then we sum up, so we group those agents into subgroups and sum up their decisions. So for example, subgroup 1 could be all people living in one town, and then this over time, this is how many people have decided to buy a PV system here. So at the first point in time, no one has one, and then maybe 5 and 10, 20, and so on. And in the next town, in the orange color here, the people decide at different points in time, and so on. And then you have a model that outputs such a quantity, and then you can decide it to, and then you can compare it to empirical data. So for example, as we did here, we use empirical data of PV systems in Germany, and we have this model output, and then we can compare it and see, okay, in the year 2000, in the real data set, almost nobody, 0% of the people had like a PV system. The model says roughly the same. And then in the year 2008, you can see different districts where people already adopted. And 2016, even more people have PV systems, and the model has like comparable output. Let's now have a look at how we actually model the diffusion of innovation. And at the very core of our model, we have such a utility function, this u of n and t. And this is a real number, and it depends on agent n, and it also depends on time t. Yeah, and it is calculated using those two quantities. So we have this vector x of n and t, and we have this vector alpha. So starting with this vector x, what is that? Let's first fix our agent. So we take some agent, n equals 1. And this agent now has attributes that somehow define the agent. So for example, maybe the agent has an income. And we take this monthly income and we maybe normalize it, and then we put it into this attribute vector. The agent could also have an environmental attitude. Let's put it in here. Maybe also the agent has friends, and the friends do have some opinion, so we also find some value that represents the opinion of the friends, and then we put it in here into this x. And yeah, what you put in here, that depends on you. You can come up with any quantity that you think is important. You put it into those agent attributes, and then you can use it in your model. And the vector alpha, that are free parameters now that we can change to make the model predictions better. And how this utility function now is calculated is actually depends on you. You can define your own function here. In our experiment, we used some rather simple function, which is just the dot product of x of n and t times alpha, meaning that we multiply this element-wise. So it's a sum over x alpha. So let's have this k. So it's the kth component of this vector, and the kth component here, and this still depends on n and t. Sorry for this notation, but I think the concept should be clear from here. So let's now have a look at how the model works mathematically. we have here the utility function we just talked about, and we see the agent attributes and the free parameters, they both go into this utility function. And yeah, the utility function is a real number between -infinity plus infinity. And down here, we have sketched some exemplary utility for example, for this blue agent here. So the utility function at t equals 0, it starts at -3, then it goes up here, and in the end it's at +3. And yeah, we already know if the utility function has a high value, then it's more likely that the agent buys the new technology. And we did achieve this by now putting this utility value into such a mapping function. So this is like such an S-shaped function that down here is at 0, up here it's at 1. So if you put in very small values of u, you get roughly 0. If you put in very large values of u, you get a 1. So this mapping function does now map the utility to an adoption probability. So this adoption probability still depends on n and t. And down here, if we put the utility from this blue agent into such a mapping function and get the adoption probability, yeah, at the beginning it's almost a probability of 0 of adopting, and at the end it's almost 1. So in between here, the agent has probably adopted. And then we do a computer simulation. We have this adoption probability. So we get the adoption state of agent n at time t, which we denote here as this y tilde. And yes, the blue agent at the first 3 points in time, this agent does not adopt. Then at time 4, it buys the new technology, or it adopts, and then yeah, it has adopted. So this quantity is 1 at this point in time where the agent actually buys the technology. We've seen now how we can model the decision process of an individual agent. But if we want to have an empirical model that we can compare to empirical data often is not at the level of individual agents, but more of like subgroup of agents. So for example, all agents from the same town, we know how this new technology diffused in this town, at which time how many people have bought the technology. So what we do there is we simply sum up the contribution of all agents. So we have here the adoption of the group G at time t, and yeah, we define groups of agents that are these groups here, and if the agent n is part of this group, then the adoption variable from agent n comes into the sum, and then for one subgroup, all these adoption variables from individual agents are summed up, and then you get adoption curves for whole subgroups. And because the individual decision depends on free parameters, of course, also this adoption process for a whole group still depends on the free parameter alpha. So we see now roughly how the model works. And of course, if you want to see further details, you can have a look at the paper. But now we come to the next point, meaning the calibration of such a model. Right now, we start probably with some random free parameters, and this produces just a random model output. And in a calibration process, you look at your model prediction and you look at real data and you compare those two. So with the figure that also comes from the paper, we have like the model prediction here. The subgroups are here now people living in one district in Germany. And the PV data tells us how many people in those districts have bought a PV system. And yeah, so you take for each district, you compare the number that is from here, and then you compare it to the number that is from here, and you see if your model is good or bad. And how is that done? Yeah, it's done with a loss function. So you define some loss function, which is simply the sum over the least square residuals. So you take the real data set, you take the difference from the real data and the model, you square this difference, and then you sum it up over all groups G and all time points T. And then you get one number, one loss number, and if this loss is very high, that means that your model is not so good, and the smaller this loss function is, the better is your model. Now we come to the point where we want to calibrate the model, meaning that we want to minimize this loss function we have defined. So we have the three parameters, and we can vary those three parameters. We could put different three parameters into our model, and then our model produces different results, and thereby the loss function, the value of the loss function changes. And we want to find a minimal loss function value by changing the three parameters. And now the core part of our paper is that such a calibration can be done using gradients. So we can actually calculate this quantity, so the gradient of the loss function with respect to one component of the vector alpha k, and then we get this rather complex looking term. But the important thing here is everything in here is well known. So we have like the data set, for example. This is the mapping function. This is the utility function we have defined. We have here the gradient of the utility function, which can also be calculated, and so on and so forth. If you're interested in how this works in here, I also recommend you to read the paper. But the essential is you can calculate the gradient of your loss function, and you can also do this numerically in your algorithm, and you get some vector, which is a gradient. Then you change your three parameters according to this gradient vector, and you have a new set of three parameters, and then you put those three parameters into your model, and then your loss function decreases. And finally, if we use those gradients in calibration, we have done this here with this example for PV system diffusion in Germany. And we've taken two more traditional approaches of gradient-free calibration methods, which are those two here. And then we have also used a gradient-based approach. And we see here the loss function L over the number of optimization steps. And yeah, we can clearly see that the loss function decreases much faster when we use gradients in our calibration. And if you now want to use such a model on your own in your next research project, yeah, you don't have to implement all that stuff from scratch. So there is this GitHub repository where you can find the code in here, and then you can copy paste the already implemented gradients and try them by yourself.